Thank you.
Большое спасибо.
Yeah, my talk is Artisanal Async Adventures. I'm going to talk about async. Importantly, I'm not going to talk about async IO, the library. I'm going to talk about async IO, the concept. I know it's a terrible talk title, but the goal of the talk is, the problem is that async has this stigma of being incredibly magical and hard to understand, and nobody knows what's going on. And my goal is to show you in 30 minutes and 100 lines of Python or less that async IO is not that magical. You can actually understand it if you understand Python or coding. And so yeah, I'm going to say the word async a whole bunch, and it's important to understand what I mean when I say async. When I say async, I'm talking about asynchronous IO, or more specifically, asynchronous network IO. So I'm not talking about some library, I'm talking about a concept of doing IO in an asynchronous fashion. Also, as he mentioned, my whole talk will be live coding, so do expect things to go wrong. And I'm going to do all my live coding in PyCharm, so if something goes wrong, it's probably PyCharm's fault, so blame them. Okay, and so to show you how async IO works, we first need a problem that needs solving. And the problem that I have is I've come up with a brilliant algorithm that will change the world. And I know that everybody on this planet wants to use this, so we have to scale massively to meet that demand. And I'm now going to share this top secret algorithm with you. By the way, everything will be in Python 3.7, and we will use type hints because I like them. So my algorithm takes an integer and returns an integer. And it will take the integer I get and add 42. Yeah? Okay. You already see how this has a pressing need that the masses have. So we want to expose this to the world, and the way you expose something to the world these days is you make a server. You put it on the internet so people can use it. So we will write a server. And our server will run on an address, will never return because it's a server. And we will just say an address is a tuple of a string, which is the interface to bind to, and an integer, which is the port to listen on. Now, we could, of course, use Flask or Django or something like that, but HTTP is way too high level and has way too much overhead for our needs here, because we really need to have like massive scalability. So instead, we will just do raw socket programming. So, oh yeah, and I will do magical PyCharm stuff sometimes, don't worry. So I just imported a socket module because we want to make a socket server. The way to do that in Python is you create a socket object, and we want to have it in the address family internet and a stream socket. So that's a TCP/IP socket. And again, because we need to scale massively, we will tell it to reuse its address when we reuse the port. I'm not 100% sure what this does, but luckily Linux Peter is just next door, so just ask them to clarify. Now with Python sockets, the way you make a server as opposed to a client is you bind it to an address, which is what we'll do, and then we tell it to listen with a certain backlog. Don't get too worried about the number 5 here. It's just something we need to tell it to make it a server. Now, because it's a server, of course, we want to run forever, so we make a while true loop. And the way in Python, if you do socket programming, to accept connections from a client is you call accept on the socket object. That will return a tuple of a client socket and the address the client is connecting from. So we will do some crappy logging. So we got a connection from the address. So that we'll see that we got a connection. Now, I could, of course, handle the client right here in my server function, but I want to decouple the code a little bit, organize my code, so we'll make a handler function and pass the client there. Now, the handler function takes a socket, the client socket, and like the server function, it will not return anything, because, once again, we want to massively scale here, so we want to make it so that the client can reuse their connection to make multiple requests. We don't just want to have one request per connection, because otherwise the connection overhead will be way too much. So we'll again make a while true loop, and we will accept data from the client so that we have a request, which is a bytes object. And the way you do that is you call receive on the socket object, tell it how much data maximum you want to receive. And now, if there's nothing in the request, we will stop. So this is how the client can tell us they're done with all their processing. We're not interested anymore. Now we need to turn this into a number. And the neat thing with Python is, even though it's a bytes object, if we send it ASCII encoded integers as a bytes object and then call int on it, it will do what you expect and turn it into an integer. And then we simply call our algorithm with that number, and we need to send it back. The way you do that is you call the send function on the socket module, and we will send the result, new line delimited, and we will encode it as ASCII. Good. Now, assuming, and that's a huge assumption, that I did not make a mistake, this should actually work. This is how you can write a socket server in Python. So let's test that and just run it. And now in another terminal, I will connect to that. And the way I will connect to my server today is using netcat, so NC. Netcat is a Unix utility that lets you connect to a TCP server and send data, and whatever data comes back, it will print. So it's really neat. And now I will need a little bit of audience participation. Could somebody give me a number between 1 and 100? 1? Yeah, and it added 42, so it's 43. Perfect. And again, we want to scale, so let's simulate a second connection in a separate tab. So if somebody else could give me another number. 30. Oops. This is kind of embarrassing. That doesn't work. So let's go back to the first connection. Let's maybe try 30 here, but it works. It's, our massively scalable, awesome server is not actually massively scalable. It can apparently only scale to 1 user. That's not really acceptable. So what happened? Python, by default, will run your code in a single process, in a single thread, top to bottom, just one instruction after the other. So when we pass the client connection to the handler function and then have a while true in here, the lower loop, the loop in the server, will never continue running until that client stops. So we need to fix it. How do we fix it? Well, Python 3 added this fantastic async await stuff, so we will make our code async. So we make async dev handler, async dev server, perfect. We now have an async, amazingly scalable application. So I run it and, okay, it just stopped. How can it stop? There's 2 while true loops in there. It should not stop. It should just keep running. And it also gives us this weird runtime warning, a coroutine. What even is a coroutine? Server was never awaited. Oh, okay. Apparently, we have to take a step back and do Python 101. So I will open an IPython shell, eventually. So if we have a function foo, and the function foo prints foo, if we call foo, it prints foo. What happens if we have an async function bar that prints bar? If we call bar, it doesn't print anything, it doesn't print bar, but it returns a coroutine object. So what is a coroutine object? In IPython, you can use underscore to get the return value of the last expression. So that's what we do. And another nice thing in IPython is if you write a variable, a dot, and then you hit tab, you will see the methods and properties of that object. So we have close, crawait, crcode, corigin, send, throw. Now, I've done you all the service, and I've read the documentation of coroutine objects. So I know that the function that we're interested in is send. If I send none to this coroutine object, 2 interesting things will happen. An exception is erased, a stop iteration exception, although we had no loops in our function at all. Interestingly, though, before it raised the exception, it printed bar. So apparently, that's how you can run a coroutine object. And again, I've read the documentation, so you don't have to do it right now. And I know that the stop iteration exception is just a way of Python, of CPython, telling us this coroutine object is done. And now comes the part where it gets a tiny little bit magical, because we will need one more building block before we can return to our code. And this, if I make a class and give this class a double underscore await method, and double underscore methods in Python, those are the magical methods that implement protocols that Python can use. And interestingly, this await method is not an async method, it's just a normal method. And if I yield something in this, and now I write an async def bar that prints pre, and then awaits an instance of that class, then we'll do just print post. Now if I get this coroutine object again, so nothing happens, just as we expect. Now if I send it none, it prints pre, and then it returns hoge. It returns the thing that our double underscore await yields because of the await statement. But it doesn't print the second print statement because of the await statement. It awaits and stops. So if we were to send none again, it raises a stop iteration because it reached the end of the function and it printed the thing after the await. Interesting. So let's see if we can use this knowledge to turn our function into actual asynchronous code. So I'm going to introduce two new APIs that we will build. One is called add_task. And add_task is what we will feed our coroutine objects. So I will implement a add_task. And from now on, I will just call coroutines task because coroutine is kind of hard to say. So I will define a type task, and we will keep that to keep track of running coroutines. I'm not going to implement it right now, but this is how it's going to look. So then we will have a run function, and the run function will actually run the tasks. Good. So we have one thing. We will implement an API to run coroutines, but the coroutines are only one part. So far, I've not talked about I/O at all, and I/O is actually what we need to talk about. Because if we want to make this code asynchronous and working so it can handle multiple connections, we need to think about where our code will block because it has to wait for I/O. Because the waiting time when we wait for I/O is the time we're interested in if we build an async system. And there's 3 points where it will block because of I/O. If we go from top to bottom, the first one is the socket receive call. That will block until the client sends us data. So we need to change this to await async receive, pass it the socket and the number. I will implement this in a second. Next, we have sock send. Send could block if this pipe to the connection to the client is blocked. So we need await async send, and then just pass it in. And the third and last place where we block is when we accept. If there's no connection to nobody that wants to connect to us, this call will just wait forever until eventually somebody connects. So we will say await async accept socket object. Now let's implement that. So we have async nef async receive takes a socket object, takes a number of bytes you want to read, and will return bytes. So we have an async send, again takes a socket object, takes some data you want to send and returns the number of bytes it sent. And then we have async accept, which will take a socket object. And once it's done, it will return a tuple of a socket object and an address. So what do we do in here? We will have a run function which will handle running everything. And we will need to tell that run function that we are actually not able to continue our work in our function until something happens. So we will say, await until we can read on the socket object. And then we will just read on it. And then for send, we will do the same. We will say await until, so this is kind of a domain-specific language. It should read a little bit like English. And await until we can read send to the socket. And then just send. And then for accept is actually a read call. So again, wait until we can send a read on socket. and then accept. So what is our await class? So we will write this, of course, ourselves. Again, we are using Python 3.7, so we will use data class. If it was not 3.7, I will use attrs. And our data class or attrs class has two attributes. It has a action and a target. And the action, we will just make an enum of either read or send. And we don't really care about the values, so we'll just use auto. By the way, this is all still standard library. And our until class has to implement await, and it will simply yield the action and the target. Now we're almost done. Now we have to actually implement the thing that will run our whole server. So our add task function, what does our add task function do? We will just make a global queue or deck of tasks. Collections.deck, if you're not familiar with that, it behaves very similar to a list. It's just optimized to add to one end and remove from the ends. So in add tasks, we will simply add the task to our list of tasks that we want to run. And the run function will run those. So while we have tasks, we will get a task, and we'll just take the leftmost task that we have. And we will then try to run it by calling send none on it. If it's a stop iteration, because again, as we saw, stop iteration means done, we will just continue. Now, if the action is that we can read, we will do something. And otherwise, if the action is that we can send, we'll do something. Otherwise, we'll raise an exception because something went terribly wrong. So, and what do we do when the coroutine or the task tells us it wants to send or it wants to read on something? We will just put it in a waiting area. So we will make a wait read waiting area, which is a dictionary of sockets as key and task as values. And we'll make a separate waiting area for tasks that want to send. So that's just dictionaries. So when our current tasks wants to read, we will put it in the wait read waiting area with the target socket as the key and the current task as value. And the same deal for if we want to send. So now we have a way to get our coroutines, run them until they cannot run anymore and have to wait for something. So we put them in a waiting area. So now we need the opposite. Now we need a way to take tasks out of the waiting area back into our active task queue as soon as they are actually able to proceed because the condition that they were waiting on has been fulfilled. And because tasks are moving out of the tasks queue all the time and going to those waiting areas, we have to change our loop up here and say while there is anything in either the active task queue or in the waiting area for reading or for sending, you keep running. So now we could have a situation where tasks is empty, so we cannot pop left from it. So while there are no tasks, we have to move them out from the waiting areas into the active queue. How do you do that? Now comes the second part that is slightly magical, where we will just defer to the kernel, as in we will leave Python a little bit and just let the operating system handle it. The Python standard library has a module called select. That select module has a function called select. If you pass this function a sequence of sockets that you want to read on as the first argument, so wait read, a sequence of sockets that you want to send to, so wait send, and a third argument that we will not care about, the select call will eventually return a triple, so a tuple of length 3, where the first element is the sockets of the weight of the sockets that you want to read on that you passed in that you can read on right now. So can read. It will return as the second element a list of sockets you can send to right now, so can send. And again, the third return value we don't care about. So now we know that there's a bunch of sockets we can read on, a bunch of sockets we can send on, so we will take those. So for socket that we can read on, we will just add it back to the task. So we will move it out of the waiting area for reading, back into the active task queue. And we'll do the same thing for the sending waiting area sockets. And there we go. And again, assuming I made no mistakes and the line numbers look correct, this should actually work. So we will simulate one client again, and let's just check 130. Okay. Somebody else with a number. 11. And there we go. We have 2 clients connected, and they can all talk. And we can even have a third one. And we could be crazy and send 42 in and get 84 back. It even works with negative numbers. Amazing. So, using nothing but the standard library and ignoring this async IO, which does this, we can build an asynchronous networking server in 100 lines of code. And now we have to talk about why does this actually work. And the core concept of this is that while we are waiting for IO, instead of just waiting and doing nothing, we will do something else. So we will keep track of all the things we want to run, all the code that we want to run. And all the code that cannot run right now because it has to wait something, we will move over there in a waiting area. And all the code that can run right now, we will run as soon as possible. So let's look at how this actually works. So if we call add task with the server and then run, add task will add the server function, the server task, into the global tasks list. So when we then run it, tasks exists, we have the task, so we will get the task, the server task, and run it. So the server will create the socket, listen, hit the while true, call async accept, and then this will signal back to our run function. The server socket wants to read on the server socket. The server function wants to read on the server socket. Good. Action is read. We put it in the waiting area for reading. And then we hit the top of the loop again. Tasks is empty now, but wait read isn't. So we call select select with the server socket as in the list of the first argument. And select will eventually, when we get a connection from a client, return that socket in the can read. So we will move it out of the wait reading area back into the active task queue. So the server task is now back in the tasks. We pop it out. Current task is server. We send none to it again. Now we are here. Now we have a client object. So we will print, create the handler task with the client, add it to the task queue, hit the while true again, and hit the await accept, async accept again. So our action is again read. Target is again the server socket. So we put the server task back into the waiting area for reading. Now our task list has the handler, the client handler function. So we don't have to hit the select code block yet. So we will run the handler function as far as we can do. While true, await async receive. So the action once again is wait for reading, but the target is now the client socket. So now we move the client task, the client handler task, into the wait read area. And now both the server task and the handler task are in the wait read area. So we hit this select select again. And now comes the part where I cannot walk you step by step through it again. Because now it depends. Is there a new connection first? Or does the client send data first? And depending on which happens, or if both happens similar, like close enough together in time, both of those will be in the can read thing list, and we'll add them to the task again. And so the tasks move from the active task queue into those waiting areas and back and forth and back and forth. And this whole thing is orchestrated by us telling it whenever we are waiting for I/O to be possible. And a very, very important part of this whole system is that you only ever have one task that is running. You don't have, with multi-threading or multi-processing, you have the problem where multiple things can run at the same time if you have enough cores and things like that. And you have to think about race conditions and locking things. And generally, if you stay away from threads in async I/O, and you cannot always do that, you don't have to think about those things because only one thing will ever run in your Python process. And now, before we finish, you might maybe think now, well, that was fun and all. You showed us something funny that works. But how does this relate to anything in reality? Well, at the very core of async I/O is this code. Not exactly this code, because they do fancy things like error handling. I mean, who needs that? I never make mistakes. So, but they do error handling, which can be nice, and they have some higher level APIs, so you don't have to actually work with sockets directly, and you don't have to call these weird functions, so you can work with it a bit nicer. But at its very core, the idea and the more or less the implementation inside async I/O is going to be the same as this, as will be Tornado and Twisted and Trio to a degree, and Node.js, by the way. Now, you might have heard of Node.js, like a lot of people like to use it. Pretty much all the async I/O, asynchronous networking systems that don't just rely on threads will use something like this. So tasks or coroutines that are either can be run right now or can be run eventually, and then a loop that just moves those tasks back and forth between waiting areas and active queues. And yeah, that's more or less it. And now I just have one bit of bad news for all of you. And that is that I have homework for you. Because part of, again, the goal of this talk was to show you that it's not an inhumane feat to implement an asynchronous system with Python using nothing than the Python standard library, ignoring async I/O. So my homework for you, and of course I will not check this, but please do it, is if when you go home, either on your way home or when you get back home from this conference, maybe sit down and try to write those 100 lines. Now you can, of course, you don't have to do it in front of a bunch of people live with a microphone and everything and with a camera. You can do it in the privacy of your own home with your own computer. You can, of course, have all the documentation you want open. You can even listen to my talk that I gave this talk at other conferences, so it's already on YouTube. So you can listen to it and just type it by yourself. The only thing I will not do is I will not upload this code somewhere for you to download and copy paste, because that's not the point. The point is that you do it by yourself. You type the actual thing and think about why you're typing what you're typing and what it does. And if you want to get extra points in this homework assignment, instead, you're not going to use select. I use select here because it has the easiest interface, and it's easiest to show you how things work. It's not actually what you would ever want to use in production. I'm not going to explain why. I'm going to let you think for yourself why that is if you're going to do the homework. So if you're on OS X, you want to use something called select.kq. It's in the standard library, nothing to pip install. If you're on Linux, you're going to want to use select.epoll. And if you're on Windows, you want to use select.devpoll. I'm not sure if those are even, no, they're not available on OS X. So try to build it with that instead of select, and try to think about why those other systems are more performant and more reasonable than just using select all the time. And with this, I am done, and I think we have some time for questions if any of you have questions. If not, thank you very much for listening.
Thank you, Jonas. Any questions? Everybody seems so impressed.
impressive live coding. I guess this is not meant to be run in production. So in your opinion, what would you choose between Trio, Curio, and asyncio in Python 3.7?
So yeah, absolutely never, you want to never, ever, ever run this in production. Jeez. This is for educational purposes only. No, I would use asyncio for a very, very simple reason. Trio may be better engineered. The nursery stuff may be something you really want. And if you have a good use case for it, use Trio. My reason for using asyncio is because asyncio has a huge hype wave behind it right now, and people are building lots of apps for asyncio, and there's a good community building around it, and you're going to get a lot of good libraries for it. So your best bet is asyncio, even if it may or may not be technically the best thing that exists right now. In the corner.
Thank you, Jonas. It was very interesting. I have another question. Yeah, seems to work.
Okay.
So there is one line that actually is the clue to. Okay, that's fine. The clue to this whole code, it is that yield stuff in the await. So basically, I think that one of like improvements to the homework could be implementing it in Python 2.7 using yield. So basically, async is a shortcut for kind of yield. And
oh yeah, I know that under the hood that there are generators.
So I didn't just ask, I wanted to elaborate on this.
That's an implementation detail that I think is not terribly interesting if you're going to use it. But yes, you can do this. You can do this code in Python 2.7. It's going to be not as pretty. It's going to be way weirder because with the async await, it clearly defines that you're awaiting. If you use the 2.7 approach, which is yield and yield from, it doesn't really signify you that you're waiting for anything. It just says yield from this function, and it looks the same as if you yield from a generator that is just a box standard Python generator. But yeah, the reason, of course, why there's a stop iteration that is being raised at some point is that under the hood, everything is a generator. Yeah.
Yeah. Thank you.
Nope.
Well, as I understand, this code utilizes only single core.
Yes.
What should be done to extend it to multiple CPU cores?
You would do the same thing you would do for synchronous code. Like, you would run it through GUnicorn or something like that. What we personally do at our work is we run everything in Docker containers, and we give each Docker container just one core. So we just spawn up more instances. Yeah, this is only using a single core, single threaded, single process. And so if you want to scale beyond a single process, you would use this exact same scaling strategies that you would use with synchronous Python code to scale it. Yeah.
Thank you.
Thank you for your talk. I'm wondering if there any reason to use threading approach for I/O operation in Python, or maybe it's better to throw it away and use only async.
So we cannot just throw away threading. For I/O, I would prefer to use async I/O whenever I can, but sometimes you use a third-party library. And for that, I would defer to Lynn's talk a couple of hours ago, where she talked extensively about how to use threading with or async I/O plus threads when you deal with third-party libraries that do their own I/O in some way. So we still need the threads to interface with third-party code or reasons like that. Yeah, don't throw away threading, we still need it.
So it's only for backward compatibility, but any performance reason, there are no performance reason to use thread instead of.
None that I'm aware of.
Okay, thank you.
Yeah, why not?
So basically, thanks for giving me the microphone. And I want to elaborate on the answer of the differences of the async I/O approach used with one-threaded code and the opposite of using threading. Because if you have one core and your application is I/O intensive, so basically this async I/O approach is working really fine. But suppose you have some computations going on. So while there are computations, the CPU core will just block everything, and the I/O is also blocked. So for that purpose, threads are used to parallelize the computations, and just that's the difference between async things and the threads. So for I/O intensive apps, definitely async I/O. And for computation intensive apps, this approach won't work. It won't scale. Thank you.
Thanks. Guess that's it. No? Oh, okay, yeah.
Uh-oh.
I have some bad news. We have a thing called a GIL in Python.
Yes.
So it's exactly the same. Like you don't get anything with threads unless you write C code.
Yeah, the nice thing about async I/O is you don't care about the GIL. It just doesn't matter.
Yeah, you could say threading is preemptive multi-threading, and this is cooperative. But other way, you gain nothing with threads unless you write C code and find a way to release the GIL.
Yeah. Yeah, the nice thing, again, there's no threads. The GIL actually helps us and makes everything faster. As soon as you use threads, as Hinek said, yeah, you fight the GIL. And many times you don't actually want threading to offload your CPU heavy stuff. You want to go even so far as to use multiprocessing, which you can also use very nicely with async I/O.
Maybe as a small tidbit, you'll need threads for async file I/O.
Yes.
Because there are APIs in all systems to do async I/O, like async new word I/O, but they do not really work. So you have to use threads for that.
Yeah. It's weird that, yeah, it's called async I/O, but it's actually only async network I/O, because none of the operating systems that exist give you asynchronous file I/O. Even if they claim they do, they don't. And yeah, you have to use threads if you want to read a file or write the file.
So now you have to pick a person, which question you think is the best, and
What? I have to pick?
yeah, and give this to them.
I don't get it. It's a mask to sleep and a coffee not to sleep. I don't know. The gentleman in the back.
Right, let's give
That's a good
Jonas a
question.
round of
Yeah.
applause.
There you go. Thank you.
Thanks.